Okay, so if in fact we're out here, if this turned out to be 115 and we're out here at 120, then we would reject the hypothesis. And again, the hypothesis is that the two advertising campaigns work the same. If in fact the new campaign is out here, then we're going to reject the hypothesis, and that means the two campaigns are different. And since the new campaign is producing more people than the old campaign, we can say, hey, we think the new campaign is better. Okay? So, in computer biz, they talk about GIGO, garbage in, garbage out. If you give us bad numbers, we'll give you bad results. And as we sit here, and I'm doing this right before the election, right? We don't know, and not right before the election, a month before the election, 2 months before the election. All the polls might be misleading. The data in the polls might be wrong. The pollsters think they know who's going to vote and how, and maybe they have the wrong data. So when they conclude that a particular state is going to a particular person, they might be having bad data in there, and then when they do their statistics, it gets a bad result because they have bad data. And we won't know until November comes along and people start voting, or I guess people start voting in October, but you know what I mean. Until election day, and election ends, and then we'll know whether the polls were right or wrong. And I think we already talked about in the last couple of videos that Barack Obama both times did better in reality than the polls said he was going to do. So there's always, the chance that the numbers are bad. All right, so we can also do hypothesis tests in two tails. And if we do them two tails, and this is 5%, how much is really in each rejection region? The answer would be, you would put 2.5% over here and 2.5% over here, right? And the table already does that for you. You don't have to figure that out. But the problem with doing your statistics this way is that it actually is only a 2.5% test, because your sample's never both below the mean and above the mean at the same time. If we do it this way, we've put all 5% out here, and when we say we're 5% chance of error, we're 95% sure, we actually mean it. But in this case, we're really 97.5% sure and only 2.5% rejection. And the idea that we could be both above and below the mean at the same time is just kind of silly. So we don't generally do two-tailed hypothesis tests. We do two-tails confidence intervals, but we only do one-tail hypothesis test most of the time because it makes a lot more sense. Okay? All right. So let's do an example. So, Firestone believes a tire lasts an average of 50,000 miles. A sample of 100 tires lasts 48,000 miles with the standard deviation of 5,000 miles. Test at 95% one-tail. So again, if your brain goes, hey, the sample had 48, this is new. But remember that the standard deviation is 5,000 miles. So there's lots of tires that ran over 50,000 miles. So maybe the mean really is 50,000 miles, and we need to find out. Okay? So, step number 1, H0, that null hypothesis. The null hypothesis is either what they believe or what the existing number is. So they want you to test whether the things are 50,000 miles. So that's your test. Are these tires, do they work 50,000 miles? The alternative hypothesis would be that the tires don't last 50,000 miles. Because the 48 is less than the 50, we could also put less than in there. Because if they're not 50, they're sure not 51 or 52 or 53. They're 48 or 49 or 47. Okay? So if they're not the 50, they're going to be less than the 50. So you could put a less than sign in here. But I always just use not equal to because then I don't have to worry about it. Okay? So we take the 50 and it goes in here. We take the 48 and it goes in there. We take the 5 and it goes in there, and we take the 100 and it goes in there, right? That's mu minus x bar s and the square root of n. Okay? So we do the math. It's 2,000 over 500. That's 4. For what? The answer is 4 standard errors. And I'm assuming you're getting used to my penmanship by now. 4 standard errors. What that means is that 50,000 and 48,000 are not 2,000 miles apart. They're 4 standard errors apart. And in statistics, that's really far. These two numbers are really far apart. Okay, so I don't even have to do the rest of the part because I know what I'm doing, and eventually you'll know what you're doing, and you won't have to do. You go 4. The tires don't last 50,000 miles. But let's do it step by step to make sure we know what we're doing. Okay, so we got the T is 4. That means the mean and the sample mean, the population mean and the sample mean are 4 standard errors apart. Okay, and we have to go find the critical value. So we exit here, we go over here. We want 1 tail 0.05. Okay, we said the alpha value is 0.05. We want to do it 1 tail. This is our t-table. We just go all the way down the bottom. Why? Because 100 is infinity. Okay, so 1.645 is the number we want. And we come back over here. And it's 1.64. It's actually 1.645, but we don't really care. It's not going to matter. Our T is 4. Critical value is 1.64. 4 is greater than 1.64. Our T is greater than our critical value. Okay? When this is case, we reject H0. We reject the null hypothesis. The tires do not last 50,000 miles. Okay? Let's go back, draw a picture. In this case, that's 48,000, that's 50,000. They're 4 apart. 1.6 is in here somewhere, 4 is out here. I have a better picture in a second, but I thought I'd give you a quick one. There's another way to calculate this, and the other way to calculate this is something called a p-value, and that's where you have Excel not look up a number in a table, but actually give you a probability. So you would take the 4, you would stick it into Excel in a thing called the t-table in Excel, the t-dist it's called. And it would tell you that the probability, this is the actual probability that the sample actually gets 50,000 miles. What's the probability that these tires actually average 50,000 miles is 0.00003. In other words, it's 3 in 100,000 chance. There's no chance that these tires actually last 50,000 miles. Okay? We don't want to do the p-value in class because we want you to do these things by hand and actually look at them and figure them out. So a lot of computer printouts, you'll see a p-value, and again, that's the probability that you associated with this hypothesis. It's got to be bigger than 5% for you to accept the hypothesis. This is way less than 5%, right? That's less than 0.05. Therefore, what do? We reject. Okay? Everybody with me? So here we are. We have 48,000 and 50,000 out here. 50,000 is out here at the critical value. 48,000. Now, let me just say that you could draw this the other way too. You could put the 50,000 here, and you could put the 48 down over here. And technically, people would tell you, oh, that's the way to do it, because it's correct. But personally, I'm right-handed. I always do these things in the right tail, and it doesn't make any difference. There are statistics nerds that are really convinced that you need to do it this way, right? But no. So this is our critical value. This is our test statistic. Our test statistic is bigger than our critical value. The 4 is bigger than the 1.64. The 1.64 says out here is the rejection region. We're in the rejection region. We reject the hypothesis. Okay? And again, how are we going to get good at this? We're gonna practice. So, you being an evil statistician want to make sure that Firestone can claim these tires last 50,000 miles. So what are you going to do? The answer is you're going to have a really small sample. So instead of doing 100 tires, you do 16 tires. So Firestone now still thinks the tires last 50,000 miles. You run a sample of 16 tires, and if you're really evil, you'd run 4 tires. But you know what I mean? A sample of 16 tires lasts 48,000 miles with a standard deviation of 5,000 miles. Now we go ahead and test this. So H0 stays the same. Firestone believes that tires last 50,000 miles. That's our hypothesis. The alternative is they don't last, or it's less than that. Now we do the math over again. Say math, 50,000 goes in, 48,000 goes in, 5,000 goes in, 16 goes in now. We do that, and we get a T of 1.6. Ooh, okay. Now, our T, which is our test statistic, is 1.6. Mu and X bar here are 1.6 standard errors apart. Critical value now is going to be 1753. Why? Because now we have a small sample. So we come back here, and again, 0.05, one tail, right? One tail, 0.05, that's this column. But we had 16 observations, so we only have 15 degrees of freedom. And that means our critical value is 1753. Hopefully everybody gets that. Okay? So the critical value is now 1753 with 15 degrees of freedom and alpha of 0.05. T is smaller than the critical value. The critical value, 1753. T is 1.6. Now I fail to reject the null hypothesis and say, look, the tires last 50,000 miles. This is why one of the famous things about statistics is that there are lies, and then there's statistics. Because a statistician, by setting up the terms of how they conduct their experiment, can sometimes influence the outcome. Good statisticians always have very large samples, are very random, do things with a certain right way, but you'll often see things done that are done the wrong way. We've seen after primaries or after certain events, there are polls that people take where they let people call in or they let people click on the internet, and no matter what statistics you do on those, they're not reliable because they're not random. Okay? So now, same thing. Here's our critical value. But now, the test statistic is here, and 50,000 is inside the acceptance region, not the rejection region. And now the tires do last 50,000 miles. But they lasted 50,000 miles because we took a really small sample. right? So a hotel believes that the mean gaming budget of its guests is $500. They survey 900 guests. That would be good, right? We'll probably do this again where they only survey 9, but they survey 900 guests and find a mean gaming budget of $470, standard deviation of $100. Again, so we have a null hypothesis. First step, null hypothesis, mu equals 500. The alternative is that mu is less than 500, or you could say not equal to, it's less than, because 470 is less than 500. We put these numbers into our equation. Standard deviation of 100, mean of 900, and we get 9, which is our test statistic. Okay? We don't have to look that up. We're statisticians. You look it up just because you got to look it up, but 9 is, it's gone. There's no chance that the actual mean is 500. It's closer to 470 than that. Okay? But we have a critical value. Again, we have the same critical value, 1.64. In the back of your mind, you're going to get burned into these numbers, 1.64 and 1.96, that we use over and over and over and over and over again. 9 is bigger than 1.64. Our z, our test statistic, is bigger than our critical value. We reject the null hypothesis. What does that mean? Our average tourist does not spend $500. Okay? So again, here's $500, and this one's in the left tail. Oh, I did it in the left tail. This is the way you're supposed to do these. 500 is there. 470 is way out here somewhere. Right? It's gone. It's 9 standard errors. That's standard error. 9 standard errors out there where the critical value is 1.6 standard errors. We're way out in the rejection region. The chance that 500 is the right answer is 1 in millions. Right? There's no way. But again, if you absolutely wanted to prove to your boss that it was 500, instead of surveying 900 guests, you'd survey 9 guests. Okay? So now we surveyed 9 guests. They have a mean budget of 470, standard deviation of 100. The null hypothesis and the alternative stay the same. We take the 500, the 470, the 100, and now we take 9 and stick it in here. And we get 0.9 as our test statistic. And now we're going to say, yeah, of course, boss, 500 is the right answer. So our critical value now, we have 9 observations, right? So let's go back. We have 1 tail 0.05. We have 9 observations. We lose 1 degree of freedom. So we have 8 degrees of freedom, which is 1.86. So we come back here. Our critical value is 1.86 with 8 degrees of freedom. 9 is less than 1.86. 0.9 rather is less than 1.86. That's our test statistic. That t is our test statistic. It's less than the critical value. We're going to fail to reject, which means, okay, that in fact in this survey, in this study, 500 works. 500 is a valid number. Okay, the tourists each spend $500. And the p-value for this is 18.4, which means the probability is 18%. So there's an 18% chance that's right. That's bigger than 5%, which is the same as this, the other way to do it.